I want to remind you that there should be three things drawn here. There should be the object, and the heavier it is, the bigger it is. There should be an arrow. The faster it is, the longer it should be. And then there should be a boundary. Okay? Then we need three labels. In this case, I need to label the 100 kilogram mass, and I need to label the velocity, 5 meter per second velocity. I'm kind of using a big font here, probably too big for this particular worksheet, but this is just...
Mr. Fairley, does it matter what direction the arrow is going in for this particular question?
No, it doesn't.
Okay, great.
And then finally, I need to label the momentum, which is this weird measurement of kilogram meters per second. So 3 parts of a diagram and 3 labels for each momentum. That's just a review. For this one, the softball player, 75 kilograms. Well, that circle should be smaller than this one. Somebody's making a bunch of noise. Can we turn off our microphones, please? Velocity, 10 meters per second. That means this arrow should be bigger than this arrow. Okay, just to keep that in mind. So these are just more practice problems. And then we did collisions. So the thing with the collisions is we have to look at both before the collision and we have to look at after the collision. And so we started with one ball colliding with another ball. Once again, we have 3 parts of the diagram: the masses, the velocities shown by an arrow, and we have a boundary. This one they drew for you. All you had to do is just fill it back in. And the nice thing about this was ball number 2 was not moving at all. So it had a velocity of 0. Ball number 1 was moving at 2 meters per second times its mass gives its momentum of 20. But over here, ball 2 not moving, 10 times 0 means it has a momentum of 0. Now the thing that might be confusing to some people, so I want to emphasize this, to find total momentum, we have to combine these two, and we just add them together. In this case, it's 20 plus 0. That's our total momentum here. However, let's imagine that this was a momentum of 1 meter per second. Let's just imagine that. It's not 0, it was 1. In that case, the momentum of ball 2 would be 10, and my total momentum would now be 30. So you multiply mass times velocity to get momentum, and then you add the momentums of the different objects to get the total momentum. If they're both moving, it becomes a little trickier than it was in this problem. Okay? Total momentum is their combined momentums. So that's the before. Now for the after situation, we have to remember that momentum is conserved. So whatever the momentum was before the collision is the same as it is after the collision. So for this problem, before I changed it around, it was 20. That means total momentum after the collision is still 20. And since these are moving together now, we just draw one arrow to show them. They're moving together. Total momentum was 20. Gm per s. The tricky part, though, is finding this velocity. That was tricky. So we had to do some algebra to figure that out, okay? So we know that this was 20 kilogram meters per second. We also know, let's see, how heavy were they? They were both the same mass. They were both 10, weren't they? Each ball had a mass of 10, which means my total mass was also 20. Now, step 2 is just showing the algebra. What I've done here is I've separated mass in kilograms from the velocities, because I'm trying to find their velocity. This is where we left off last class, so this is probably already done. But we need to be able to do this in the future, so I wanted to walk through it again. So I'm going to take both sides of the equation and divide by this 20 kilograms. I'm going to divide this velocity by 20 kilograms so it cancels out, and I'm left with just the velocity. Over here, I'm going to divide this 20 kilograms by this 20 kilograms. They just happen to be the same number. Well, 20 divided by 20, pretty easy division there. My answer is they are now moving at 1 meter per second. So I would label this as 1 meter per second for my velocity arrow. The combined mass was 20 kilograms. That's because each of them had a mass of 10. Let's see, I think I'm just going to change this to a smaller font. Right, combined mass was 10 plus 10, which makes 20. That's where I got this 20 kilograms from. The 20 kilogram meters per second momentum, that's because it was conserved from the before condition. Remember, I changed this. This was actually 20. This was actually 0. Right? I just brought this momentum down here. Because it's conserved, it's the same after as it was before. It happened to be the same number as their combined mass, which gave us 1 meter per second velocity. Of course, the last thing I had to do was draw the boundary of the system. Okay? So that takes us to page 15. And page 15, we're going to repeat this process, but we're going to make it one step more complicated. And that is because we're looking at Newton's cradle now. We're going to go back to Newton's cradle, where we had 5 objects, not just 2. Fortunately, it's not so difficult because only one of the 5 is actually moving for this analysis. So let's see. In Newton's cradle, the balls moved in the same direction. One ball stopped, and the second ball began to move. Let's see what conservation of momentum has to share. Well, we didn't actually see the second ball move because it immediately got stopped by the third ball, which itself was stopped by the fourth, which was also stopped by the fifth, and then the fifth ball actually moved, right? So imagine that this is the cradle where the balls are moving. M1, ball number 1 with its mass, that's why it's M1, comes swinging into the system, hits these guys that are not moving, which moves this one out. So once again, we're going to start with only analyzing the system before the collision. After we do that, we'll analyze the system after the collision. Okay? So, each ball has a mass of 5 kilograms. We're going to say that ball number 1 came swinging in here with a velocity of 2 meters per second. Right? So here's ball number 1. I'm just going to copy and paste that. Four more times. There's ball 2, ball 3, ball 4, ball 5. Each of those balls had the same mass. And this says it was 5 kilograms. So I'm going to take this and I'm going to add that label down here. And once again, here, and once again here, because they're all the same, right? All of these had the same mass. One thing I thought was incomplete here. It says M2 equals 5, but this is supposed to be talking about all of those other balls as well. So I'm going to add M3 equals M4 equals M5 equals. Now I've said that all 4 of these balls have a mass of 5 kilograms. Now, what I would like you to do on your own is find the momentum. Here's the mass, here's the velocity. You calculate momentum. Here's a hint for you. Up at the top of the page. You calculate, fill in the momentum. Same thing over here. Find the momentum of balls 2, 3, 4, and 5. Of course, they're not moving, so this one should be really easy. Then you have to find the total momentum. To find the total momentum, you add the 5 momentums together. Again, this should be pretty simple.
Yes.
We need to show the movement of the first ball. So I'm going to add that arrow. I need to label its velocity. What was that? 2 meters per second. So there's that. I need to draw the boundary of the system that they've shown for us. Let's see, have I drawn 3 things? The mass is involved, the movement involved, and the boundary. Yes, I've done that. Have I labeled 3 things? I've labeled the masses, I've labeled the velocity. One thing missing that I still need to label is the total momentum. So that's going to be whatever you calculated right here. And again, you're going to repeat a bunch of numbers because so many times we're just adding 0 or multiplying by 0.
Mr. Fairley?
Yeah.
I'm a little slightly confused. So the first ball, we're just doing the regular calculation. Ball 1?
Yeah.
So that would be the whatever that is, right? Which is the momentum.
You just multiply. Yep.
Okay.
For
Now,
balls 2,
what I'm
3,
confused about, what I lost track of, was this ball 2, 3, 4, 5.
Well, we could have done this 5 or 4 times.
Yeah.
But since they're all the same mass, since they all have the same velocity, we're only doing it once.
Okay, so basically you're doing the same formula, and it comes out, all of them come out to the same end result.
Whatever you get here, which should be nothing.
Yeah, exactly.
So they're just taking a shortcut. That's going to go there. It's also going to go, you know, every time you're going to put the same thing in there for ball 3, for ball 4, for ball 5. It's always the same thing.
Same thing.
Because they all have the same mass, they all have the same velocity. You just repeat that over and over again.
Okay, and
the only one that's different is ball number 1.
Okay, so 5 is basically going to be the same. Doesn't 5 move?
This is before the collision.
Oh, before. Hello. Okay, gotcha.
Yeah, this is before the collision.
Yeah.
So we're only calculating the momentum entering the system, and none of these are moving, so they have no momentum. So our total momentum is basically whatever you got over here from ball number 1, isn't it?
Yeah.
We just keep adding 0 to it. But in a more complex situation, you could do this same thing. So for instance, if there was a collision between two cars, the police investigating the accident could calculate the momentums of the two cars and
Oh,
figure out from their momentum how fast they were moving. If we can find out how heavy they are, we can find out how fast they are based on their momentum. So there's
that,
lots of ways we can make use of this information. An engineer would make use of this stuff to calculate the amount of fuel needed to move a rocket, for instance.
that makes sense.
Okay, so at this point, you should have three things labeled: the masses, the velocity, and the total momentum. You should also have three things drawn: the objects, and there are 5 of them, the boundary, and the velocity. This time, only one object is moving, really makes this much simpler problem. Now, we're going to move on to what happens after the collision. Please let me know if I'm moving too fast. I'm thinking that this was pretty simple because we had this 0 in here. 0 times 5 gives 0 momentum, so you just add 0 to whatever number 1 was, and you're done. So, what does the velocity of mass 5, ball number 5, what does its velocity have to be after the collision to maintain conservation of momentum? We're going to draw the vector diagram. We're going to outline the boundary of the system and all of that. Okay? So let's remember, first of all, that after the collision, imagine what a Newton's cradle looks like. This is before. I think we should actually start with our diagram. So I'm going to click on one of these circles. I'm going to copy it. I'm going to come down here and I'm going to paste it in.
So when you copy it, where do you have your cursor to copy it? Just right in this.
It has to be activated. So right now, this is not
Right.
activated. So
Okay.
I just click on the edge of it, left click on the edge, then I control C, then I control V.
Oh,
And I
okay.
can control V 5 times or 4 times, and I'm going to get all the balls that I need to draw Newton's cradle. There are 5 balls, so I need to show them all in my diagram. I want you guys to think about this for a minute. This is after the collision. So imagine this is Newton's cradle. I'm not going to draw them the way they're supposed to be because I want to see that you do this for yourself. This is before we drop it, right? Here's the ball. Think about Newton's cradle. I lift this one up and it comes swinging in here from the outside, right? That's this ball that's swinging in. Yeah? These 4, they're just hanging there, aren't they? They're not moving at all. Please don't do these lines on yours. I'm just showing you, I'm just trying to help you think about what it looks like. That was a bit much, wasn't it? But okay. This one, on the other hand, is coming in at an angle, isn't it? And it's going to slam into those balls. This is what it looks like before it hits, at the moment before it hits. But the diagram that we used only showed the balls without showing the strings that they're hanging from. So I'm just trying to help you visualize that. Imagine that this is what it really looked like. But now I want you to do the same thing down here, showing what it looks like after the collision. So ball number 1 has now hit the other balls. And as you know, the momentum has been transferred from the first ball to the second, to the third, to the fourth. to the 5th. So think about the first swing. That's what you're really drawing. Remember when we measured how high the ball went? We dropped it from one side. The ball swings up on the other side, doesn't it?
Yeah.
And we measured how high it went. That's what you're going to draw. Imagine that you paused the video at the moment that this ball was swinging out. What would this look like then? Which balls would you put next to each other? Which balls would you separate? Remember, we've only dropped one. So how many respond? Some of these should be touching. Some of them should not be touching. Just like on our initial diagram, these 4 were touching. And this one was not, because it was swinging in from the outside. So I'm just trying to give you a bunch of hints if you're not sure what I'm talking about. Imagine that this is, I paused the video just before the collision. And then you pause the video just after the collision when this ball goes swinging out. That's what you're drawing down here. What does it look like when we pause the video when this one has gone swinging out? Okay, so you're going to need to arrange these circles to show that. I don't think I've arranged them properly yet.
Is the momentum the same as the one above?
Absolutely, because of
the
conservation of momentum. We're not doing the math yet. Right now, I just want them to visualize what's going on by drawing the way the balls should be. I also want you to add an arrow. This arrow, of course, is showing the movement. And I want you to think back to the Newton's cradle. When we dropped it, only this one was moving. At the moment that we pause it, because this ball is swinging up, how many balls are moving? And that answer would be how many balls you put this arrow onto. Again, we only dropped one. So how many respond? You should know that. So some of these should be drawn touching. Some of them should be separate. I'm not telling you how many. I will tell you we only dropped one. And you should show the correct number responding down here. Of course, we also need a boundary to this system. Of course, we need to label each of the masses. And the masses haven't changed, right? They didn't lose any mass, did they? Once again, they only said ball 1 has a mass of 5, but actually all of the balls have the same mass. M5, ball 5 is over here. The other 4 balls are over here. That should give you another hint of what your diagram should look like. They all have the same mass, and so we need to label that down here, correct? For each ball. Now let's think about this. When this ball comes swinging into the cradle, it has momentum and these others do not. But then it hits this ball and transfers the momentum to the end, which basically pushes this ball up out of the cradle. But every time this one transferred its momentum, it lost momentum and sat there for a moment. Same thing with this one. It took the momentum and just passed it on, passed it on, passed it on. Well, this one didn't have anybody to pass it to, so it moved. But all of these guys stood still for a moment. All 4 of those, balls 1 through 4, all stood still for just a moment. So once again, we're back to 0 velocity for all 4 of them. At least in a perfect Newton's cradle, that's what we would see.
Oh, so that's 0 there.
Absolutely.
Oh, wow.
These guys pass their momentum on. So they're not moving. They gave the momentum away. Only this ball is moving at the end, right? Isn't that what we saw? If we
Oh,
drop one
yeah.
ball, then one ball rises up. It would be different if we dropped two balls, but we're in this diagram, we're simplifying the simplest situation. We drop one ball, it gives its momentum to the next ball, which just gets transferred on down. The only one that ends up moving is this one by itself. So all of these guys have no velocity, which really makes this a simple math problem because momentum is 0 times 5, right?
Yep.
I see a mistake here. This needs to be crossed off. That should not be there. That should only be talking about the
5.
momentum of ball 5 by itself. Actually, I'm going to put a square on top of it because I don't want that to show at all. You guys can do that too if you like. That's an error. I'm going to make this, I know, I can make it filled in with white. And I can give it a white boundary. And then it will just hide that entire mistake. Sorry about that. Should have proofread it more closely. This is what it should look like. See how I just put a white box on top of that stuff? That should not be there. So if you've got that there, get rid of it. We're only talking about the momentum of ball 5 on this side. We're going to talk about the momentums of the other 4 balls on this side, which of course, since they're not moving, at least for a moment, a fraction in time, they're not moving. They have a momentum of 0. Now this problem, since it's after, we already know the total momentum because we calculated it up here. In fact, we wrote it down over here, right? Should be something like 10. Whatever the momentum was at the beginning, because of conservation, is the same as the momentum at the end. So whatever your total momentum was on this diagram, you should have the same momentum here. And no, I'm not giving you all these answers. You got to think about some of this stuff for yourself. I'm telling you how to get the answer. Whatever it was here, which was also right here, which was actually also right here, because all these other guys had a momentum of 0. Whatever it was here, it should be the same thing here. Total momentum is conserved. So you should be able to fill this in. So now we're kind of working backwards. Maybe I'm going to do this. I'm going to say the momentum is X. I'm not going to tell you what it is. You should be able to figure it out. It's simple. Whatever that X happened to be, it is the same down here. Because of conservation of momentum. And because of that, we can figure out the momentum of ball number 5. Given that these momentums have to be 0, right? Don't these have to be 0? 5 times 0 is 0. Doesn't that mean that this has no momentum? This one has no momentum.
Hello.
This one has no momentum. This one also has no momentum. The only momentum is in ball number 5.
Oh, yeah, thank you. That's for you, Dad.
A little distraction. So whatever the momentum was in these 4, it was 0. which means my total momentum is totally dependent on the momentum of ball number 5. But wait a minute.
What's the box?
If this was momentum X, sorry. There. Whatever this momentum was, X, again, we got it from up here. Because momentum is conserved before and after the collision, it's the same. I'm calling it X. I know that all these guys have a momentum of 0 because 5 times 0 gave me 0. You should be filling this in. I'm not going to do it for you. That means that all of these can kind of be canceled out because they all 4 had 0 momentum. Which means my total momentum after was only from ball number 5. Which means that ball number 5 also had this momentum of X. Which is going to allow me to figure out this velocity. Because I know P equals M times V, that means that if I want to find velocity, all I have to do is P divided by M is going to give me the velocity. This is just algebra. I'm canceling out the mass on this side by dividing it, but that means I have to divide this side by the mass also. So all you have to do now to find this velocity is take this number and divide by M. It should give you the velocity. And that velocity, since everything is conserved, you can tell if you did this correctly or not, because that velocity should be the same as the beginning velocity before the collision. Whatever the velocity was there, that's the same velocity you should get on the outside. Didn't we see that with the Newton's cradle? Well, not quite, but we saw that it was almost the same. Because we didn't have a perfect cradle, some of that velocity was lost. But we're trying to imagine a perfect cradle for this math. So none of the velocity was lost. So ball 5 should have the same velocity coming out of the system that ball 1 had going into the system. Now let's see. The diagram. You've got to position these balls correctly. You've got to put the arrow on the correct ball. You've got to label all their masses. You've got to label the velocity of this arrow, which is going to be over here. You have to label the total momentum, P equals, and I've just been calling it X, but you should have that number over there. We already drew the boundary, we drew the objects, and we drew the arrow. Just got to put the arrow in the right place. I'm not going to tell you where to put it, though. It should look like a Newton's cradle that you have paused at the moment that we've had a response. Okay, so I want to go back here, and I would like to find out if anybody has any questions or if this is all good. Are we making okay progress here? Are you staying with me? If I'm not hearing anything from you, then I'm going to assume that it's okay. All right. Okay, so nobody's written me a note, nobody's talking to me. I assume that we've got this diagram figured out. We've got these numbers figured out. It's really simple math for this example, especially because so many times we use 0. That really simplifies everything. Let's look at the final page of the project. This one should be pretty easy for you to do. It's just a review of how to calculate momentum and drawing a momentum vector. So I'm not going to do this one with you. I'm going to leave you to do that one on your own. Now, notice question 6 has several parts. A, B, C, D, E, F. Okay. And this one is about a collision. So it's a little trickier. It's about a collision of 2 trains. And it's a little trickier because they have different masses. With the Newton's cradle collision, we were using the same number. So you got to keep these straight. They have different masses. They also have different velocities. You can go ahead and fill these in while I'm talking. Let's work on this together right now. Come back to number 5 on your own later. So fill in the mass for the first train car. Fill in the velocity for the first car. And find its momentum. Go ahead, pull out your calculator if needed. Do your multiplication for momentum. Then we're going to do the same thing for the second car. Fill in its mass. It's in front of the first car. It is not moving. Oh, that's handy. That means velocity must be 0 if it's not moving, huh? How nice is that? It's not moving. It has 0 meters per second velocity, and that makes momentum easy to figure out, doesn't it? Okay. Then it asks us to draw a vector diagram of these 2 cars before they collide. I'm going to use a box to represent them. Let's see. The first car was bigger than the second. So I'm going to draw a bigger square for it. It was bigger in terms of its mass, right? It's probably actually the same length, but it's heavier. So I'm going to show that by making a bigger box for it. And of course, I have to label its mass, blank, you get to fill this in, kg. Same thing for this one, for car number 2. Blank kg, fill that in. Go back to the correct problem to figure that out. Let's see, what's next? That's the masses. Next, I need velocity. This one was moving at 10 meters per second. So I need an arrow showing that the first one is actually moving. So I'm going to put that arrow right there to show it's moving. And of course, I have to label how fast it's moving. And once again, I'm going to let you do that for yourself, blank meters per second. Let's see, the second train car, oh, it's not moving. I don't need an arrow for it at all, do I? We could do this problem. What if this front car was moving at 5 meters per second, a little slower? Wouldn't there still be a collision? We could do a problem like that, and I bet you guys could successfully solve that too. But we don't need to this time because it's not moving. Let's see, what else do I need? I need a boundary on my system, right? So I'm going to have that be my boundary. I've got the boundary, I've got the objects, I've got the vector. I've labeled their masses, I've labeled how fast it's moving. The only thing I have to do to finish is write down my total momentum. How do I find total momentum? Add the two momentums together, which is going to be easy because this one should have been 0. So that's what this first one should look like. Take a minute to get caught up on all of that. And then they collide. And we want to calculate their momentums. Train car 1 collides with train car 2. Train car 1 stops. That's going to be handy. If it's not moving, that's going to make our math a lot simpler. Train car 2 moves forward. What is the momentum of train car 1 after the collision? Well, let's see. Momentum was mass times velocity. So first thing I have to do, find train car 1. Here's its mass. I have to copy that down here. It has the same mass it had before. Velocity of train car 1. Oh, it stopped. That's easy. What's its velocity if it's stopped? And therefore, what is its momentum? Okay. 6e. If momentum is conserved, what will the momentum of train car 2 be after the collision? What will its velocity be after the collision? Okay, so first thing we have to do, remember mass times velocity gives momentum. Mass 2. Let's go back. Train car 2. Oh, here's the mass. So you just fill that in down here for mass 2, huh? Now on this one, we have to work backwards. So we skip on the velocity for a second. We go to momentum 2. Momentum is conserved, which means whatever you had here is going to be the same there, isn't it? So you just copy that down. Then, since we've already got this one, what was that one? I think it was 20,000 K, huh? 20,000 kilograms. Whatever this momentum was, it's the same here. To find velocity, we have to work backwards. Well, since we multiply to find momentum, working backwards means we need to divide. So to find velocity, I have to take momentum divided by mass. And we're going to find a different velocity here than here. For some of these other problems, we've always had the same velocity coming in as we had going out. But this one's going to be different because the cars, the train cars, are two different sizes. So imagine a really big train car collides with a really small car. It transfers all of its momentum to the small car. Doesn't that mean it's going to be even faster than the original car was moving? Since it has less mass, it's going to end up with more velocity in order for the two momentums to end up equaling one another. So to calculate that, momentum divided by mass will give the velocity of the second car. And I'm giving you this hint that it should be more than the velocity of the first car. And the final thing you're going to do on your own is draw the momentum vector of these two train cars after they collide. I'm going to let you do this one all by yourself now. It's just these two cars. I want to remind you that train car number 1 has now stopped. Train car number 2 is moving forward. So you need to draw the two train cars. You need to, just like we did here, label their masses. You need a vector arrow to show which cars are moving and which are not moving. Put the arrow on the car that is moving and label how fast it's moving. Draw the boundary and label the total momentum, which again, total momentum was conserved. Whatever went in is the same amount that comes out. Okay. Does anybody have questions before I turn you loose?
No.
Okay, thanks, Diego. It's nice to get an answer. I hope that makes sense. We've basically finished our study of momentum, and we should be looking for a test on Friday so that we don't have to remember it all over Christmas break. So once again, the test would have two parts, of maybe about 20 multiple choice questions, and then some problems to solve, some momentum vectors to diagram, some momentum problems to solve, and basically your best study tool is going to be this right here. I will also make a practice test and post it on Teams for you to work with. Let's see, on the test, we're not going to have multiple objects like this Newton's cradle one. It will only be two things that collide when we do a collision. Not every problem will be about a collision. There will be some that are just like this, where all you have to do is find a momentum of two things. So the test is basically a review of everything that we've done here, right? We should be familiar with this vocabulary. Be really helpful to understand that vocabulary for the multiple choice questions. Maybe review this reading would be another good thing to do, okay? I mentioned the 3 laws here. We're not going to go into that in detail. Let's see, for Newton's cradle, basically, what are the big ideas about Newton's cradle? That momentum is conserved. No matter how many balls we drop, the same number rise up on the other side. No matter the height we drop them from, they rise up the same height, well, almost, on the other side, if it was a perfect cradle. So those are the kinds of things you'll be doing on your test. Nothing new, but I will make a practice test for you and get that posted on Teams so you're ready. If you have any questions about what we were talking about here, or about how to do this problem, it's just basically a review question that's the same as the problems on page 13. Or what was happening with these trains that we ended with. If you're lost on that, stick around. Otherwise, you're free to go and finish the assignment and turn it in. It is due today. Unit 3 project due today. Thank you for being here.
Hey, Mr. Farley.
Maybe I'll just see you soon. But you're free to leave. Unless you have questions, stick around.
I do.
Yeah.
Thank you.
Hey,
Bye.
by the way, I'm getting a plumber's coming over to check out our irrigation. He should be here in like 10 minutes. I'm not sure how long it is, so I'm not sure if I'll chime into 7th, but I did chime into 6th. So